Welcome to day 2 of 100 AP Physics 1. Today we're going to focus on the relationships between position, velocity, and acceleration. Let's start with position. Position is the length between an object and reference point. We typically measure position in meters. You see this written as m often. And the variable we use is x. However, there's another big concept with position, and that's the idea of displacement. Displacement is the change in position. We usually write this as delta x, which equals the final distance minus the initial distance. However, sometimes you might see delta x written as s in some cases, but it means the exact same thing. Now let's move on to velocity. Velocity is the change in position over time. Or you could say displacement over time, as displacement is just change in position. We typically measure this in meters per second, written as m over s. The variable we use for velocity will be v. And now let's move on to acceleration. Acceleration is the change in velocity over time. We often measure this in meters per second, which is written as m over s, or you can simply write it as meters per second squared. The variable we use for this will be a. One thing you might notice about all these, again, is that they're all vectors. This is important because it matters if they're in the positive direction or the negative direction. And remember that you define that direction. Now let's move on to the basic graphing relationships between them. So first, when we look at these graphs, we'll notice two things. They have a slope and an area. For a position versus time graph, we'll look at the slope. The slope will simply be delta x over delta t as its rise over run. And what is change in position over time? That is simply velocity. Now let's look at a velocity versus time graph. We'll also look at the slope, which will be change in velocity over change in time, which if you notice, that will be acceleration. Now let's look at the area under this graph. Let's say we're going from this time to this time. It will be this area. And what do you think this will be? This will actually be the displacement of the object. You can think of this as if you were to take this equation and move the delta t over, you'll get that delta x equals v times the time. Now let's look at the acceleration versus time graph. We don't analyze the slope for this graph, instead we analyze the area under the curve again. So we go from this time to this time, we'll use this area, and what do you think this will represent? This will represent the change in velocity. Like how we did with the position versus time graph and the velocity versus time graph, you can see that with this equation, you can move it over to get change in velocity equals acceleration times time. So the slope of a position versus time graph will get you velocity, and the slope of velocity versus time graph will get you acceleration. The area of acceleration versus time graph will get you velocity, and the area of a velocity versus time graph will get you displacement. However, sometimes for the position versus time graph, you won't get a simple linear line. Sometimes you'll get a quadratic line. So how do we analyze the slope of a quadratic graph? Well, we can analyze the slope under a very small change in time. So let's say we have this time and this time. This will be a really small change in time. And we can say that the slope between these 2 points is like this. Now we can do this over multiple of these, and we get that the slope at this point looks something like this. So as we can tell, the slope is increasing. This will surprisingly turn into a linear relationship with velocity. Now for acceleration, we say that velocity is changing consistently, so it'll just be a simple positive acceleration. However, you won't only see a quadratic that is increasing. You'll see different versions of this. So let's analyze all of these. So we can analyze the little small slopes we have. So at this point it's around here, at this point it's around here, and at this point it's around here. So then the slope, the velocity starts at 0, and it's increasing constantly. Now for this graph, let's do the same thing. The slope at this point is about this, the slope at this point is about this, and the slope at this point is about this. So then the graph is starting at a positive velocity, and it's decreasing down to 0. Now let's do the next graph. So at this point, our slope is about this. At this point, our slope is about this. And at this point, our slope is about this. So our velocity is actually starting at 0, and it's going negative. Now let's look at this graph. Let's do the same approach where we look at the slopes at different points. So in this case, the velocity is starting negative, and it's approaching 0. This quadratic to linear relationship might come up, so it's important to understand this. So now let's go into some practice questions. The graph shows the accelerations of object 1, a1, and objects 2, a2 as a function of time. Which of the following correctly relates the magnitudes of the change of velocities of object 1 and object 2, delta v1 and delta v2 respectively? So how do we find the change of velocity from an acceleration versus time graph? Right, we use the area under the curve. So let's start with object 1. Object 1 is this top one, so the area under the curve will be this entire area. Now let's look at it for object 2. This is object 2, and this time the area is on only this part. So in this case, the area under the curve for object 1 is greater than the area under the curve for object 2. Therefore, A will be the correct answer. Now let's move on to a velocity versus time graph. The graph shows the velocity of object 1, v1, and object 2, v2 as a function of time. Which of the following correctly relates the magnitudes of the acceleration of object 1 and object 2, a1 and a2 respectively? So how do we find the acceleration from a velocity time graph? Right, we use the slope. For object 1, we use rise over run, and in this case, our slope will come out to negative 2 meters per second. Now let's look at object 2. This is object 2, and we use the same process of rise over run. In this case, we get positive 2 meters per second. So then you might immediately think that B will be correct because the acceleration of object 2 is greater than the acceleration of object 1. However, the question asks for the magnitudes, which only includes the measurement or the number in this case, not the direction. So in actuality, the answer is C, the accelerations are equal. Continuing with the velocity versus time graph, we have the velocity of 3 planes are graphed as a function of time. Which of the following correctly relates the magnitude of the displacement of each of the planes? So how do you find the displacement from a velocity time graph? You use the area under the curve. So we're going for till this time. So now let's see how big the areas are. We have this area, we have this area, and we have this area. So the area of plane 1 and plane 2 are equal, but the area of plane 3 is bigger. So then D will be the correct answer. It doesn't matter that the velocity is decreasing for plane 2, since it's still positive. Because if you think about this, if a ball is just decreasing in velocity, but it's still moving in the same direction, it's still gaining a position over time. Now in this one, we have a position versus time graph. The graph shows position x of an object as a function of time t. Which of the following correctly describes the motion of the object? The object undergoes a constant non-zero acceleration from t0 to t1. So how do you find the acceleration from a position versus time graph? Well, first we have to analyze the velocity to get the acceleration. So how do you find velocity from a position versus time graph? In this case, let's draw a graph. So from t0 to d1, we have a consistent slope, therefore the velocity will be consistent. So then what's the acceleration of a velocity that is constant? The acceleration will be 0. Therefore, A is not correct as the acceleration is 0. Now for B, the object has a positive velocity from t0 to t3. So in order to find the velocity from a position for the time graph, what do? We look at the slope. So in this case, the slope is positive, which means it has a positive velocity. But at this case, the slope is negative, which means the velocity is negative. Therefore, B cannot be true. Now for C, the object has a constant velocity from t1 to t2. So we see that the slope of the position for the time graph from t1 to t2 is constant, which means that the velocity is constant. However, let's look at D for practice. The object has a constant velocity from t2 to t3. So let's look at the slope of this graph. So we see from here, the slope is this much. At this point, the slope is about here, and at this point, the slope is about here. So as we learned earlier, if the velocity is increasing, that means there is an acceleration, which means that the object does not have a constant velocity, which makes D incorrect. All the questions that we saw only have the positive axis, but let's see a question that has a negative y-axis as well. The velocity of a cart is represented by the graph above. Which of the following is most nearly the displacement of the cart from t0 to t3? So how do you find the displacement from a velocity versus time graph? We use the area. However, in this case, we can't simply do the area really easily from t0 to t3, so we can break it up into multiple shapes. So let's break it up into a triangle, and a rectangle. And then what we do is we just add them all up. For this first triangle, we do 1/2 base, which is the base is about 1, times height, which is 3. Then we add the other shapes. We do 1/2 base, which is about 1, 2. However, the height is negative in this case, so we can just write -2. You can do this in a way where you can say the -2 will be positive and make the whole area negative. As you know, the area under the curve, if it's in the negative axis, will be negative. However, we can also just simply put -2. Now for the rectangle, we do base times height, which you can do 1 as the base and -2 as the height. Adding this up will get you about -2. So then D will be the answer. Another type of question you could also see is a question where you have to produce a graph from a given graph. The figure above shows the velocity of an object as a function of time. Which of the following graphs could represent a possible graph of the object's position as a function of time? So for these questions, I recommend instead you draw your own graph and then you compare it to the options so you don't get biased. So let's draw our own graph on the side over here. So let's draw our axes with position on the y-axis and time on the x-axis. So let's break this up into different parts. So how do we find the position from velocity versus time graph? We look at the area under the curve. So for this part right here, we have this area. So how to draw a graph of the position if the velocity is constantly decreasing? We have to use the quadratic relationships I shown you earlier. So for this section, for this type of graph with a velocity that is decreasing, we have to draw a quadratic that looks like this. So let's just start at the origin, for example, because you can start anywhere because you don't know where you start at your point. You only know the change. Now let's look at this second part. So we look at the area under the curve. And in this case, if we have a velocity that's increasing at a constant rate, we have a graph of a quadratic that's constantly increasing. So a graph that looks something like this so far. Now for this section, we have a consistent velocity, which means the position will be consistently increasing. So now we just have a graph that looks like this. For this section, we can use this part. Notice that the velocity is constantly decreasing, which will mean that the position is evening out towards not gaining anything, which will result in something like this. Now for this section, the velocity is constantly decreasing, so then we'll have a quadratic function that looks like this. Now for this last section, we have a constant negative velocity, which will look something like this. So out of all these graphs, number C looks the most like our answer. So that's it for the simple relationships between position, velocity, and acceleration. I hope to see you in the next video.